This assessment allows us to begin thinking about how we might use the Dieckmann condensation in synthesis. So this molecule, diethylpimolate, will undergo a Dieckmann condensation, but how would we make it? And so looking at this, we can kind of do this combination of working backwards, but keeping in mind where we're going. Since we have a diester here, a very likely last step we would do is a Fischer esterification. And so that's going to allow us to work backwards to a dicarboxylic acid containing 7 carbons. Note that we've numbered our carbons 1 through 7, and we'll continue to do that here, so that it becomes pretty apparent that what we need to do with either of these molecules, we'll start with the one on top, is we need to get an oxygen installed at carbons 1 and carbon 7, and then we need to oxidize it further. So how would we put a hydroxyl group at carbon 1 and carbon 7? We learned back in the alkenes chapter that if we want to make the least substituted alcohol, we can do a hydroboration reaction. And so with 2 equivalents of borane, because we want the reaction to happen twice, plus treating oxidatively working it up with sodium hydroxide and hydrogen peroxide, that will give us the diol that is shown here. 1, 2, 3, 4, 5, 6, 7. So we would end up with that diol. Now we know that from this diol, we can oxidize primary alcohols all the way up to the carboxylic acid using chromic acid. In water, we'll often see that written as sodium dichromate, sulfuric acid, and water. Either one of those should oxidize these primary alcohols all the way up to the carboxylic acid. Now, using chromic acid is not the greenest way of doing this synthesis. So what we could do instead is do a Swern oxidation to an aldehyde and then a Pinnock oxidation to the carboxylic acid. I'm pausing here in case I messed this up. So let's put the reagents for the Swern oxidation. Remember, order of addition is going to matter here, but what we're going to do is we'll take DMSO, shown here, oxalochloride, triethylamine, do this reaction at low temperature, and this will ultimately, if it happens on both sides, will make a dialdehyde. Let's count our carbons to make sure we still have 7. 1, 2, 3, 4, 5, 6, 7. We can now do the Pinnock oxidation to convert this dialdehyde into the diacid. The reagents for the Pinnock oxidation are NaClO2, and we buffer that with sodium dihydrogen phosphate. Usually T-butanol is present as well. But when we do this, we convert this dialdehyde into the dicarboxylic acid, which we can then do the esterification. I notice we didn't show reagents here. Let's show those reagents: ethanol and sulfuric acid, and probably heat to give us this diester. So this would complete the synthesis if we started with this dialkene. What if we had started with this? Well, I'm going to change colors because our structures are going to overlap a little bit. It'll be a tiny bit confusing. But we can go from this alkene directly to this aldehyde using ozonolysis. And so if we take our green arrow and go down here to that molecule, we can do step 1, ozone. We can do a workup with dimethyl sulfide, and that will give us this dialdehyde. And so this combination of reactants should give us this dialdehyde, which we can then do the Pinnock oxidation to make the acid, and again, complete the synthesis with the Fischer esterification. This is how we would make diethylpimolate. There are probably other combinations of reactions you can use, but these will certainly work.